terminal window, you would actually use a simple line of command once you've actually connected to your Docker environment, and that command will be docker pull with the image name and any associated tags around that image. What that will then do is pull the image from the Docker repository, whether that's a public repository or a private one. Now, in reverse, if you want to be able to update the Docker image with new information, you do a push command where you would take the script that you've written about the Docker container that you define and push it to the repository. And as you can imagine, the commands for that are also fairly simple. In terminal window, you would write docker push the image name, any associated tags, and then that would then push that image to the Docker repository. Again, either a public or a private repository. So if we recap, the Docker file creates a Docker image that's using the build commands. A Docker image then contains all of the information necessary for you to be able to execute the project. Using the Docker image, any user can run the code in order to create a Docker container. And once a Docker image is built, it's uploaded to a registry or to a Docker Hub where it can be shared across your entire team. And from the Docker Hub, users can get access to the Docker image and build their own new containers.
I'm Anjali from Simplilearn, and I'll be taking you through the installation process for Docker. So now let's begin with the demo. We'll be installing Docker on an Ubuntu system. So this is my system. I just opened the terminal. So the first thing you can start with is removing any Docker installation that you probably already have present in your system if you want to start from scratch. So this is the command to do so. Sudo apt-get remove docker engine docker.io. Enter your password and Docker is removed. So now we'll start from scratch and we'll install Docker once again. Before that, I'll just clear my screen. Okay, so before I install Docker, let me just ensure that all the softwares on my system currently is in its latest state. So sudo apt-get update. Great, so that's done. Next thing, we'll actually install our Docker. So type in sudo apt get install Docker. Now as you can see here, there's an error that's occurred. So sometimes it's possible that due to the environment of the machine that you're working in, this particular command does not work. In which case, there's always another command that you can start with. Just type docker install. And that by itself will give you the command you can use to install Docker. So as it says here, sudo apt install docker.io is a command that we will need to execute to install Docker. And after that, we'll execute the sudo snap install docker. So sudo apt install docker.io first. And this will install your Docker. After that's done, we will have sudo snap install docker. So snap install docker installs a newly created snap package. They are basically some other dependencies for Docker that you'll have to install. Of course, since this is the installation process for the entire Docker IO, it will take some time. Great, so our Docker is installed. The next thing we do, as I mentioned earlier, is that we need to install all the dependency packages. So the command for that is sudo snap install docker. Enter your password. So with that, we have completed the installation process for Docker, but we'll perform a few more stages where we will test if the installation has been done right. So before we move on with the testing for Docker, let's once again just check the version that we have installed. So for that, the command is docker version. And as you can see, Docker version 17.12.1 CE has been installed. Next thing we do is we pull an image from the Docker Hub. So docker run hello world. Now hello world is a Docker image which is present on the Docker Hub. Docker Hub is basically a repository that you can find online. So with this command, the Docker image hello world has been pulled onto your system. So let's see if it's actually present on your system now. The command to check this is sudo docker images. And as you can see here, hello world repository, this is present on our system currently. So the image has been successfully pulled onto the system, and this means that our Docker is working. Now we'll try out another command. Sudo docker ps -a. This displays all the containers that you have pulled so far. So as you can see here, there are 3 hello world images displayed, and all of them are in exited state. So I did this demo previously too, which is why the 2 hello worlds which is created 2 minutes ago is also displayed here. And the first hello world which has been created a minute ago is the one we just did for this demo. Now, as you have probably noticed that all the hello world images over here, all these containers are in the exited state. So when you give the option for docker ps -a, where -a stands for all, it displays all the containers whether they are in exited or running state. If you want to see only those containers which are in their running state, you can simply execute sudo docker ps. Sudo docker ps. And as you can see, no container is visible here because none of them are in running state. And with that, we come to an end of our Docker installation.
This is Matthew from Simplilearn. In this presentation, we're going to go through a number of key things. We're going to compare Docker versus traditional virtual machines and what are the differences and why you'd want to choose Docker over a virtual environment. We'll go through the advantages of working with Docker and the structure and how you would build out a Docker environment. And during that structure, we'll dig through the components and the advanced components within Docker. At the end of the presentation, we'll go through some basic commands and then show you how those basic commands can be used in a live demo. So with all that said, let's get started. So let's first of all compare Docker with a traditional virtual machine. So here we have the architecture on the left and right of a traditional virtual machine versus a Docker environment. And there are some things that you'll probably see immediately that are big differences. One is that the virtual environment has hypervisor layer, whereas the Docker environment has a Docker engine layer. And then in addition to that, there are additional layers within the virtual machine. Each of these really start compounding and creating very significant differences between a Docker environment and a virtual machine environment. So with a virtual machine, the actual memory usage is very high, whereas with a Docker environment, the memory usage is very low. If we look at performance, virtual machines, when you start building out particularly more than one virtual machine on a server, the performance starts degrading and starts getting poorer, whereas with Docker, the performance always stays really good. This is largely due to the lightweight architecture used to construct the Docker containers themselves. If we look at portability, virtual machines just are terrible for portability. They're still dependent on the host operating system, and there's just a lot of problems that happen when you are using virtual machines for portability. In contrast, Docker was designed for portability, so you can actually build solutions in a Docker container environment and have the guarantee that the solution will work as you have built it, no matter where it's hosted. Finally, boot up time. The boot up time for a virtual machine is fairly slow in comparison to the boot up time for a Docker environment, which is almost instantaneous. So we look at these in a little bit more detail. One of the other challenges that you have with a virtual machine is that if you have unused memory within the environment, you cannot reallocate that memory. So if you set up an environment that has 9 gigs of memory that's being used, but you have 6 gigs that are free, you can't do anything with it. Though that whole 9 gig has been allocated to that virtual machine. In contrast with Docker, if you have 9 gigs and 6 gigs becomes free, that free memory can then be reallocated and reused across other containers used within that Docker environment. Another challenge is running multiple virtual machines in a single environment can lead to instability and performance issues, whereas Docker is designed to run multiple containers in the same environment and actually gets better the more containers you run in that hosted single Docker engine. Portability issues with a virtual machine is the software can work on one machine, but then when you move that VM to another machine, suddenly some of the software won't work because there are some dependencies that haven't been inherited correctly. Whereas Docker itself is designed specifically to be able to run across multiple environments and to be deployed very easily across systems. And again, the actual boot up time for a VM, it just takes a long time. You're talking about minutes in contrast to the milliseconds that it takes for a Docker environment to boot up. So let's dig into what Docker actually is and what allows for these great performance improvements over a traditional VM environment. So Docker itself is an OS virtualized software platform, and it allows IT organizations to really easily create, deploy, and run applications as what are called Docker containers that have all of the dependencies within that container very easily. And the container itself is really just a very lightweight package that has all the instructions and dependencies such as frameworks, libraries, bins, etc., all within that container. And that container itself can then be moved from environment to environment very easily. If we were to look in our DevOps lifecycle, the place where Docker really shines is in deployment, because when you're actually at the point of deploying your solution, you want to be able to guarantee that the code that has been tested will actually work in the production environment. But in addition to that, what we often find is that when you're actually building the code and you're actually testing the code, having a container running the solution at those stages is also a really good plus, because what happens is that the people building the code and testing the code are able to validate their work in the same environment that would be used for the production environment. So really, you can use Docker in multiple stages within your DevOps cycle, but it becomes really valuable in the deployment stage. So let's look at some of the key advantages that you have with Docker. Some of the things that we've already covered is that you can do rapid deployment, and you can do it really fast. The environment itself is highly portable and was designed for that in mind. The efficiencies that you'll see will allow you to run multiple Docker containers in a single environment as compared to more traditional VM environments. The configuration itself can be scripted through a language called YAML, which allows you to be able to write out and describe the Docker environment that you want to create. This in turn allows you to be able to scale your environment very, very quickly. But with all of these advantages, probably the one that is most critical to the type of work that we're doing today is security. You have to ensure that the environment you are running is a highly secure but highly scalable environment. And I'm very pleased to say that Docker takes security very seriously. So you'll see it as one of the key tenets for the actual architecture of the system that you're implementing. So let's look at how Docker actually works within your environment. So Docker works, there is what's called a Docker engine. The Docker engine is really comprised of
two key elements. You have a server and a client, and the communication via the two is via REST API. The server, as you can imagine, has the instructions that are communicated out to the client and instructs the client on what to do. The connection between the client and the server, the communication, is via a REST API. On older systems, you can take advantage of the Docker Toolbox, which allows you to go ahead and control the Docker engine, the Docker machine, Docker Compose, and Kitomatic. So let's now go into what the actual root components, though, of Docker are. So let's have a look at those key components. There are four components that we're going to go through. We have the Docker client and server, we have Docker images, we have the Docker registry, and the Docker container. We're going to step through each of these one by one. So let's look at the Docker client and server first. So the Docker client and server is a command line instructed solution where you would use terminal on your Mac or command line on your PC or Linux system to be able to issue commands from the Docker daemon. The communication between the Docker client and the Docker host is via a REST API. So you can do similar communication such as a Docker pull command, which would send an instruction to the daemon, which would then form the interaction of pulling in the correct components, such as an image or container or registry, to the Docker client. The Docker daemon itself is actually a service which actually performs all sorts of operating and performance services. And as you'd imagine, the Docker daemon is constantly listening across the REST API to see if it needs to perform any specific requests. If you want to trigger and start the whole process, what you want to do is use the command docker within your Docker daemon, and that will start all of your performances. And then you have a Docker host, which actually runs the Docker daemon and registry itself. So now let's look into the actual structure of a Docker image. So a Docker image itself is a template which contains instructions for the Docker container, and that template is written with a language called YAML, and YAML stands for yet another markup language. It's very easy to learn. The Docker image itself is built within that YAML file and then hosted as a file in the Docker registry. The image is really comprised of several key layers. And you start with your base layer, which will typically have your base image. In this instance, it's your base operating system, such as Ubuntu. And then you would then have layer of dependencies above that. This would then comprise the instructions in a read-only file that would become your Docker file. So let's actually go through and look at what one of those sets of instructions would look like. So here we have four layers of instructions. We have a from, pull, run, and then command. So what does that actually look like in our layers? So to break this down, the from creates a layer which is based on Ubuntu. And then what we're doing is we're adding in files from the Docker repository onto that base command, that base layer. And then what we want to be able to do is then say, okay, what are the run commands so we can actually then build the container within the environment. And then we want to be able to then have a command line that actually executes something within that container. And in this instance, the command is to run Python. So one of the things that we will see is that as we set up multiple containers, each new container is a new layer with new images within the Docker environment. Each container is completely separate from the other containers within your Docker environment. So you're able to create your own separate read-write instructions within each layer. What's interesting is that if you delete a layer, then the layer above it will also get deleted. So what happens when you pull in a layer, but something has changed in the core image? What's interesting then is that the actual main image of itself cannot be modified. Once you've copied the image, you can then modify it locally, but you can never modify the actual base image itself. So here are some callouts for the components within a Docker image. So the base layer are in read-only format. The layers can be combined in a union file system to create a single image. The union file system saves memory space by avoiding duplication of files. And this allows a file system to appear as a writable, but without modifying the file, which is known as a copy on write. The actual base layers themselves are read-only. So to be able to get around this structure within a Docker container, the Docker environment itself uses what's known as a copy on write strategy within the images and the containers themselves. And so what this allows you to do is you can actually copy the files for better efficiency across your entire container environment. The copy and write strategy does make Docker super efficient, and what you're able to do all the time is keep reducing the amount of disk space you're using and the amount of performance that you're taking from the server. And that's really, again, a key element for Docker, is just this constant ability to be able to keep improving the efficiency within the actual system itself. All right, so let's go on to item number 3, which is the Docker registry. So the Docker registry itself is the place where you would host and distribute the different types of images that you have created or you want to be used within your environment. The actual repository itself is just a collection of Docker images, and those Docker images are built on instructions that you would write with YAML and are very easily stored and shared. And what you can actually do is you can actually associate specific name tags to the actual Docker images themselves. So it's easy for people to be able to find and share that image within the Docker registry itself. One of the things you actually see as we go through the demos, you actually see us actually using the tag name, and you'll see how it is an alphanumeric identifier and how we actually use it to actually create the actual container itself. One of the things you can do to as start off how you would manage a registry is you can actually use the publicly accessible Docker Hub registry, which is available to anybody, but you can also create your own registry for your own use internally. The actual registry that you create internally can have both public and private images that you create, and this may be for various reasons of how you structure your environment. The actual commands you would use to actually connect to the registry are both push and pull. Push is to actually push a new container environment that you've created from your local manager node to the remote registry, and a pull allows you to pull a new client that has been created and is being shared. So again, pull command, it pulls and retrieves a Docker image from the Docker registry and makes it very easy for people to share different images consistently across teams. And a push command allows you to take a new command that you've created, a new container that you've created, and push it to the registry, whether it's Docker Hub or whether it's your own private registry, and allow it to be shared across your teams. Some key did you knows in Docker registry, deleting a repository is not a reversible action. So if you delete a repository, it's gone. So let's go into the final stage here, which is the actual Docker container itself. So the Docker container itself is an executable package of applications and its dependencies bundled together. So it gives all the instructions that you would have for the solution that you're looking to run. It's actually really lightweight, and again, this is because of the redundancy that's built into how you structure the container, and the container itself is then inherently also extremely portable. What's really good about running a container, though, is that it does run completely in isolation. So you're able to share it very easily from group to group, and you are guaranteed that even if you are running a container, it's not going to be impacted by any host OS peculiarities or unique setups as you would have in a VM or a non-containerized environment. The actual memory that you have on a Docker environment, they can be shared across multiple containers, which is really useful. Typically, when you have a VM, you would have a defined amount of memory for each VM environment. The challenge you start running into, though, is that you can't share that memory, whereas with Docker, you can easily share the memory for a single environment across multiple containers. The actual container is built using Docker images, and the command to actually run those images is a run command. So let's actually go through a basic structure of how you would run a Docker image. So you go into terminal window and you would write in Docker run Redis, and then it would run a container called Redis. So we're going to go in, and if you don't have the Redis image locally installed, it will then pull it from the registry. Then the new Docker container Redis will be then available within your environment, so you can actually start using it. So let's look at why containers are so lightweight. They're so lightweight because they really have being able to get away from some of the additional layers that you have in virtualization within VMs. And the biggest one is the hypervisor and the need to run on a host operating system. Those are two big elements. So if you can get rid of those, then you're doing great. So let's look at some of the more advanced concepts within the Docker environment. And we're going to look at two advanced components. One is Docker Compose and the second is Docker Swarm. So let's look at Docker Compose. Docker Compose is really designed for running multiple containers as a single service. And it does this by running each container in isolation, but allowing the containers to interact with each other. As was stated earlier on, you would actually write the Compose environment using YAML as the language in the files that you would create. So where would you use something like Docker Compose? So an example would be if you are running an Apache server with MySQL database and you need to create additional containers to run additional services without the need to start each one separately. And this is where you would write a set of files using Docker Compose to be able to help balance out that demand. So let's now look at Docker Swarm. So Docker Swarm is a service that allows you to be able to control multiple Docker environments within a single platform. So what you actually are looking at doing is within your Docker Swarm is we're treating each node as a Docker daemon, and we're actually having an API that's interacting with each of those nodes. There are two types of node that you're going to be getting comfortable working with. One is the manager node and the second is the worker node. And as you'd expect, the manager node is the one sending out the instructions to all of the worker nodes. But there is a two-way communication that is happening. The communication allows for the manager node to be able to manage the instructions and then listen to and receive updates from the worker node. So if anything happens within this environment, the manager node can react and adjust the architecture of the worker node so it's always in sync. It was really great for large scaled environments. So finally, let's go through what are some of the basic commands you would use within Docker. And once we've gone through all these basic commands, we'll actually show you a demo of how you'd actually use them as well. So if we're going to go in, probably the first command is to install Docker. And so if you have yum installed, you just do yum install Docker and you'll install Docker onto your computer. To start the Docker daemon, as you want to do systemctl start Docker. The command to remove a Docker image is docker rmi and then the image ID itself. And that's not the image name, that's the actual alphanumeric ID number that you want to grab. The command line to download a new image is docker pull and then the name of the image you'd want to pull. And by default, you're going to be pulling from the Docker default registry that will then connect to your Docker daemon and download the images from that registry. The command line to run an image is docker run and then the image ID. And then we have the, if we wanted to pull specifically from Docker Hub, then we would have docker pull and then the image name and colon its tag. To build an image from a Docker file, you would do docker build-t and then the image name and colon tag. To shut down the container, you would do docker stop container ID. The access for running a container is docker exec it container ID bash. So we've gone through all the different commands, but let's actually see how they would actually look, and we're going to go ahead and do a demo. So welcome to this demo where we're going to go ahead and put together all of the different commands that we have outlined in the presentation for Docker. First is just to list all of the Docker images that we have. So we do sudo docker images and we enter in our password. And this will now list out the images that we've created already. And we have 3 images there. So let's go ahead and pull a Docker image. So to do that, we'll go ahead and type sudo docker. And actually, we don't want to do image. We want to select pull. And then the name of the image that we want to pull, which is going to be MySQL. And by default, this is actually going to go ahead and use the latest MySQL command, MySQL image that we have. So it's now going to head and pull this image. It's going to take a few minutes depending on your internet connection speed. It's kind of a large file that has to be downloaded. So we'll just wait for that to download.
You can see the others have completed. Just waiting for this last file to download. Almost there. Once that's done, what we're going to go ahead and do is we'll actually run the Docker container and create the new container using the image that we just downloaded, but we have to wait for this to download first. Alright, so the image has been pulled from Docker Hub. And let's go ahead and create the new Docker container. So we're going to do sudo docker run -d -p 0.0.0.0 :80 :80, and then we'll put in MySQL latest, so we have the latest version, and we have our new token, and that shows our new Docker container has been created. Now let's go ahead and see if the container is running, and we'll do sudo docker ps to list all the running containers, and what we see is that the container is not listed there, which means it's probably not running. So let's go ahead and list out all of the images that we have within Docker so we can see whether it's actually listed there. So we'll do ps-a, and yes, there we are. We can see that we do have our new container, MySQL latest, and it was created 36 seconds ago, but it's in the exited mode. So what we have to do is we have to change that status so it's actually running. So let's change that to running state. Bash, and that's now going to be in the root, and we'll exit out of that. And now if we list out the Docker containers, we should see it is now an active container. Sudo docker start, and then we'll start the saying it, and we should now see it. There we are. It's now in the running state. Excellent. And we can see that it was updated 6 seconds ago. We're going to go ahead and we're going to clear the screen. Okay, now what we want to do is remove the Docker container. So what we're going to do is check list of images that we have. And so sudo docker images. Here are the images that we have, and we have MySQL is listed. And what we want to do is delete MySQL. And to do that, we're going to type in sudo docker rm-f image MySQL. Run that command, and what we'll find is the image. There's no such image. Oh, okay. So what we actually have to do is we have to go and see that the image is now gone. It's been removed. Excellent. It's exactly what we wanted to see. And we can also delete an image by its image ID as well. However, if an image is running and active, we have to kill that image first. So we're going to go ahead and we're going to select the image ID. We'll copy that, and it's going to, we paste that. It won't be able to actually run correctly because the image is active. So what we have to do now is stop the image, and then we can kill it. So it's in the running state. So we have to do, so we do sudo docker kill and just kill SL, and that will kill the container. And now we'll see that the container has gone. And now we can delete the image. And that's going to be the image gone with the image ID. Ba-boom. Easy peasy. Okay, let's go ahead onto the next exercise, which is to, so here we are, we've listed all of the containers and they're all gone. So let's go on to the next exercise, the final exercise, which is to actually create a batch image. And we're going to do a batch HTTP image. So let's go ahead and write that out. So it's going to be docker run -d dit dash dash name white, that's going to be the name of this HTTP service, dash p 8080:80 dash v, open quotes, $ pwd, close quotes, colon, slash usr, slash local, slash apache2, slash htdocs, slash httpd semicolon 2.4. Run that. Put in our password again. So what we see is the port is already being used. So let's go ahead and see which ports. Let's go see if we can change the port or see what ports are running. So let's do sudo images and see which ports are being used, because it's either the port or the name hasn't been put in correctly. So sudo docker images ps sudo docker ps-a, and yep, there's port 80 there. So we'll clear the screen. So we're going to change the container name, because I think we actually have the wrong container name here. So let's go in and change that, and we'll paste that in, and voila. There we go. Now working, and we'll just double check and make sure everything's working correctly. So to do that, we'll go into our web browser, and we'll type in, as soon as Firefox opens up, type in localhost :8080, which was the port that we created. And there we are. It's a list of all the files which shows that the server is up and running. Today we're going to cover what is a Docker container, why you would want to consider using it in your DevOps environment. So let's have a look at what we have in our current environment. So today, when you actually have your standard machine, you have the infrastructure, you have the host operating system, and you have your applications. And then when you create a virtual environment, what you're actually doing is you're actually creating virtual machines, but those virtual machines actually are now sitting within a hypervisor solution that sits still on top of your host operating system and infrastructure. And with a Docker engine, what we're able to do is we're able to actually reduce significantly the different elements that you would normally have within a virtualized environment. So we're able to get rid of the bins and so we're able to get rid of the guest OS, and we're able to eliminate the hypervisor environment. And this is really important as we actually start working and creating environments that are consistent, because we want to be able to make it so that it's really easy and stable for the environment that you have within your dev and ops environment. Now, critical is getting rid of that hypervisor element. It's just a lot of overhead. So let's have a look at a container as an example. So here we actually have a couple of examples. On the right hand side, we have different containers. We have one container that's running Apache Tomcat with Java. A second container is running SQL Server in a Microsoft.NET environment. The third container is running Python with MySQL. These are all running just fine within the Docker engine and sitting on top of a host OS, which could be Linux. It really could be any host OS within a consistent infrastructure. And you're able to have a solution that can be shared easily amongst your teams. So let's have a look at an example that you'd have today if a company is doing a traditional Java application. So you have your developers working in JBoss on his system, and he's coding away, and he has to get that code over to a tester. Now, what will happen is that tester will then typically in your traditional environment then have to install JBoss on their machine and get everything running and hopefully set up identically to the developer. Chances are they probably won't have it exactly the same, but they're trying to get it as close as possible. And then at some point, you want to be able to test this within your production environment, so you send it over to a system administrator who would then also have to install JBoss on their environment as well. Yeah, this just seems to be a whole lot of duplication. So why go through the problem of installing JBoss 3 times?
And this is where things get really interesting, because the challenge you have today is that it's very difficult to almost impossible to have identical environments if you're just installing software locally on devices. The developer's probably got a whole bunch of development software that could be conflicting with the JBoss environment. The tester has similar testing software, but probably doesn't have all the development software. And certainly the system administrator won't have all the tools that the developer and tester have, their own tools. And so what you want to be able to do is kind of get away from the challenge you have of having to do local installations on 3 different computers. And in addition, what you see is that this uses up a lot of effort, because when you're having to install software over and over again, you just keep repeating doing really basic foundational challenges. So this is where Docker comes in, and Docker is the tool that allows you to be able to share environments from one group to another group without having to install software locally on a device. You install all of the code into your Docker container and simply share the container. So in this presentation, we're going to go through a few things. We're going to cover what Docker actually is, and then we're going to dig into the actual architecture of Docker and kind of go through what Docker container is and how to create a Docker container. And then we'll go through the benefits of using Docker containers and then the commands, and finalize everything out with a brief demo. So what is Docker? So Docker is, as you'd expect, because all the software that we cover in this series is an open source solution, and it is a container solution that allows you to be able to containerize all of the necessary files and applications needed to run the solution that you're building. So you can share it from different people in your team, whether it's a developer, tester, or system administrator. And this allows you to have a consistent environment from one group to the next. So let's kind of dig into the architecture so you understand why Docker runs effectively. So the Docker architecture itself is built up of 2 key elements. There is the Docker client, and then there is a REST API connection to a Docker daemon, which actually hosts the entire environment. Within the Docker host and the Docker daemon, you have your different containers, and each one has a link to a Docker registry. The Docker client itself is a REST service, so as you'd expect, a REST API that sends command line to the Docker daemon through a terminal window or command line interface window. And we'll go through some of these demos later on so you can actually see how you can actually interact with Docker. The Docker daemon then checks the request against the Docker components and then performs the service that you're requesting. Now, the Docker image itself, all it really is a collection of instructions used to create a container. And again, this is consistent with all the DevOps tools that we have. The DevOps tools that we're looking to use throughout this series of videos are all environments that can be scripted. And this is really important because it allows you to be able to duplicate and scale the environments that you want to be able to build very quickly and effectively. The actual container itself has all of the applications and the dependencies of those applications in one package. You kind of think of it as a really effective and efficient zip file. It's a little bit more than that, but it's one file that actually has everything you need to be able to run all of your solutions. The actual Docker registry itself is an environment for being able to host and distribute different Docker images among your team. So say, for instance, you had a team of developers that were working on multiple different solutions. So say you have a team of developers and you have 50 developers and they're working on 5 different applications. You can actually have the applications themselves, the containers, shared in the Docker registry. So each of those teams at any time check out and have the latest container of that latest image of the code that you're working on. So let's dig into what actually is in a container. So the important part of a Docker container is that it has everything you need to be able to run the application. It's like a virtualized environment. It has all your frameworks and your libraries, and it allows the teams to be able to build out and run exactly the right environment that the developer intended. What's interesting though is the actual applications then will run in isolation, so they're not impacting other applications that using dependencies on other libraries or files outside of the container. Because of the architecture, it really uses a lot less space, and because it's using less space, it's a much more lightweight architecture. So the files, the actual folder itself is much smaller, It's very secure, highly portable, and the boot up time is incredibly fast. So let's actually get into how you would actually create a Docker container. So the Docker container itself is actually built through command line, and it's built of a file and Docker image. So the actual Docker file is a text file that contains all the instructions that you would need to be able to create that Docker image. And then we'll actually then create all of the project code within inside of that image. Then the image becomes the item that you would share through the Docker registry. You would then use the command line, and we'll do this later on, select Docker run and then the name of the image to be able to easily and effectively run that image locally. And again, once you've created the Docker image, you can store that in the Docker registry, making it available to anybody within your network. So something to bear in mind is that Docker itself has its own registry called Docker Hub, and that is a public registry, so you can actually go out and see other Docker images that have been created and access those images. As your own company, you may want to have your own private repository, so you want to be able to go ahead and either do that locally through your own repository, or you can actually get a licensed version of Docker Hub where you can actually then share those files. Now, something that's also very interesting to know is that you can have multiple versions of a Docker image. So if you have a different version control, different release versions, and you want to be able to test and write code for those different release versions because you may have different setups, you can certainly do that within your Docker registry environment. Okay, so let's go ahead and we're going to create a Docker image using some of our basic Docker commands. And so there are essentially really, kind of just two commands that you're going to be looking for. One is the build command, and another one is to actually put it into your registry, which is a push command. So if you want to get a image from a Docker registry, then you want to use the pull command, and a pull command simply pulls the image from the registry, in this example using nginx as our registry, and we can actually then pull the image down to our test environment on our local machine. So we're actually running the container within our Docker application on our local machine. We're able to then have the image run exactly as it would in production. And then you can actually use the run command to actually use the Docker image on your local machine. So just a few interesting tidbits about the Docker container. Once the container is created, a new layer is formed on top of the Docker image layer. It's called the container layer. Each container has a separate read-write container layer, and any changes made in that Docker container is then reflected upon the particular container layer. And if you want to delete the container layer also gets deleted as well. So, why would using Docker and containers be of benefit to you? Well, some of the things that are useful is that containers have no external dependencies for the applications they run. Once you actually have the container running locally, it has everything it needs to be able to run the application. So there's no having to install additional pieces of software, such as the example we gave with JBoss at the beginning of the presentation. The containers are really lightweight, so it makes it very easy to share the containers amongst your teams, whether it's a developer, whether it's a tester, whether it's somebody on your operations environment. It's really easy to share those containers amongst your entire team. Different data volumes can be easily reused and shared among multiple containers. And again, this is another big benefit, and this is a reflection of the lightweight nature of your containers. The container itself also runs in isolation, which means that it is not impacted by any dependencies you may have on your own local environment. So it's a completely sandboxed environment. So some of the questions you might ask is, can you run multiple containers together without the need to start each one individually? And you know what? Yes, you can with Docker Compose. Docker Compose allows you to run multiple containers in a single service. And again, this is a reflection on the lightweight nature of containers within the Docker environment. So we're going to end our presentation by looking at some of the basic commands that you'd have within Docker. So we have here on the left-hand side, we have a Docker container and then the command for each item. We're actually going to go ahead and use some of these commands in the demo that we're going to do after this presentation. You'll see that in a moment. But just, some of the basic commands we have are committing the Docker image into the container. Kill is a, standard kill command to, terminate one or more of the running containers so they stop working. Then restart those containers. But certainly you can look at all of the commands here and try them out for yourself. So we're going to go ahead and start a demo of how to use the basic commands to run Docker. So to do this, we're going to open up terminal window or command line, depending whether you're running Linux, PC, or Mac. And we're going to go ahead, and the first thing we want to do is see what our Docker image lists are. So we can go sudo docker images, and this will give us, well, first we'll enter in our password. So let's go enter that in. And this will now give us a list of our Docker images. And here are the Docker images that have already been created in the system. And we can actually go ahead and actually see the processes that are actually running. So I'm going to go ahead and open up this window a little bit more, but this will show you the actual processes and the containers that we actually have. And so on the far left-hand side, you see under names, we have learn, simply learn, b_cool. These are all just different ones that we've been working on. So let's go ahead and create a Docker image. So we're going to do sudo docker run -d -p 0.0.0.0 :80:80 Ubuntu, and this will allow us to go ahead and run an Ubuntu image, and this will run the latest image. And what we have here is a hash number, and this hash number is a unique name that defines the container that we've just created, and we can go ahead and we can check to make sure that the container actually is present. So we're going to do sudo docker.ps, and this actually shows on there. So it's not in a running state right now, but that doesn't mean that we don't have it. So let's list out all the containers that are both running and in the exit state. So let's do sucker ps-a, and this lists all the containers that I have running on my machine. And this shows all the ones that have been in the running state and in the exit state. And here we see one that we just created about a minute ago, and it's called learn. And these are all running Ubuntu, and this is the one that we had created just a few seconds ago. Let's open it up, and there we go. So let's change that to that new Docker container to a running state. So scroll down, and we're going to type sudo docker run -it -name my. So this is going to be the new container name. It's going to be my Docker. So this is how we name our Docker environment. And we'll put in the image name, which is Ubuntu. And -bin -bash. And it's now in our root, and we'll exit out of that. So now we're going to go ahead and start the new my Docker container. So sudo docker start my, and we'll get the container image, which will be my Docker, return, and that started that Docker image. And let's go ahead and check against the other running Docker images to make sure it's running correctly. So sudo docker ps, and there we are. Underneath name on the right hand side, you actually see my Docker along with the other Docker images that we created. And it's been running for 13 seconds. Quite fast. So we want to rename the container. Let's use the command sudo docker rename. We can take another Docker image. Let's grab this one and we'll put it in rename. And we'll rename, and we'll put in the old container name, which is image, and then we'll put in the new container name, and let's call it purple. So now the container image that had previously been called image is now called purple. So we do sudo docker ps to list all of our Docker images. And if we scroll up, and there we go, purple. How easy is that to rename an image? And we can go ahead and use this command if we want to stop a container. So we're going to write sudo docker stop, and then we'll have to put in the container name, and we'll put in my Docker, the container that we originally created, and that image has now stopped. And let's go ahead and prove that. We're going to list out all the Docker images, and what you see is that it's not listed in the active images. It's not on the list on the far right hand side. But if we go ahead and we can list out all of the Docker images, so you actually see it's still there as an image, it's just not in an active state, it's what's known as in an exit state. So here we go. And there's my Docker, it's in an exited state. So that happened 27 seconds ago. So if we want to remove a container, we can use the following command. So sudo docker rm for remove my Docker, and that will remove it from the exited state. And we're going to go ahead and we're going to double check that. And yep. Yep. It's not listed there under exit state anymore. It's gone. And there we go. That's where it used to be. All right, let's go back. So if we want to exit a container in the running state, so we do sudo kill and then the name of the container. I think one of them is called yellow. Let's just check and see if that's going to kill it. Oops, no, I guess we don't have one called yellow. So let's find out the name of a container that we actually have. So sudo docker kill. Oh, we're going to list out the ones that are running. Oh, okay, there we go. Yellow isn't in that list, so let's take simply learn. And so we can actually go ahead and let's write sudo docker kill simply learn. And that will actually kill an active Docker container. Boom, there we go. And we list out all the active containers. You can actually see now that the simply learn container is not active anymore. And these are all the basic commands for Docker container.
Today we're going to dig into Docker Swarm. So what we're going to do in this session is we're going to go through what Docker and Docker Container is and why you'd want to use it. We'll then break out what are the characteristics and structure of a Docker Swarm environment. And then finally, we'll go through and do a demo using actual code in the command line interface to actually run and build out the main functions and commands that you would use for a Docker Swarm environment. So with that said, let's get started. So Docker is a tool that we actually use to help automate applications in our environment so that we have a consistent way that we're actually building and testing and validating codes that's being created. Think of it as a virtualization, but much more sophisticated and efficient way of doing virtualization. The thing that you have that's a huge advantage when you're working with Docker is that it's a very lightweight software package. It allows you to have all of the tools needed for actually running the code without having to have the significant overhead that you would normally have with virtualization. So one of the characteristics you have with Docker is that you can actually run multiple Docker environments in the same host environment. And for you to be able to do this, we had to figure out how this would actually run. And so to actually do this, we actually do what's called a Docker Swarm. And a Docker Swarm is an environment where you can actually have multiple Docker images running on the same host operating system. So you can have running in each of those Docker containers different solutions. So let's dig into what a Docker Swarm is. So a Docker Swarm is essentially a tool that allows you to very easily create and schedule multiple Docker nodes. So really 2 or more Docker nodes. And you can have quite a large number of Docker nodes in a single swarm. Each node itself is actually a Docker daemon, and that daemon is able to then interact with the Docker API and have all the benefits of being a full Docker environment. One of the other advantages you have is that each Docker container within the swarm can then be deployed and managed but as a node in that entire clustered environment. So what we have here is a breakdown of the 5 key elements within a Docker environment. You have the Docker container, you have the daemon, the Docker images, and the Docker client and Docker registry. So the Docker daemon itself is what does all the work interacting with the actual host operating system to be able to manage the Docker containers. So if we look here we have set up an environment where we have 3 Docker containers being run with Docker. And what we want to be able to do is be able to interact with the environment, because what would happen if we actually have something change in our environment? So we have the environment set up as a Docker Swarm and one of our containers fails. What we're able to do is use the swarm to be able to correct that failure. So the Docker Swarm manager is able to come in and reschedule containers. And as you would imagine, the actual Swarm node has full backups and full redundancy for any kind of failures that would happen. And we would do all of this work through command line interface. So let's go through some of the features that you have within the actual Docker Swarm itself. So a key feature for Docker Swarm is that it is fully decentralized, which means that it makes it very easy for teams to be able to access and manage the environment. As you would expect as well, is that the communication that happens between the manager and client nodes within the swarm is highly secure. And of course, this is really just a fundamental that you should have for any kind of solution, but it is good to know that Docker Swarm has that built in. There is also auto load balancing within your environment, and you can actually script that into how you write out and structure your swarm environment. And that load balancing then also allows you to then convert that swarm environment into a highly scalable infrastructure. And then rollback task allows you to be able to roll back environments to previous safe environments. So if, say, something does get pushed out and something breaks, you're able to immediately roll back into a safe environment. So each of the containers are pushed out and are controlled using services, and they actually happen to be REST services, which make it very easy for you to be able to integrate within your environment. And each of the different services contains a group of containers of the same image. Now, by having this structure, it allows you to be able to scale your application appropriate to the demands on your service. So if you have a service that needs to have a significantly larger number of services for it to run, you can actually scale that appropriately, and that can be either geo or demand based. One of the requirements for setting up a Docker Swarm is you must have at least one node deployed. So the way that the architecture is set up is that you have a manager node and a client node, and there must be one of each for the entire environment to be able to work effectively. So, here we are just jumping ahead of ourselves a little bit. We have 2 types of nodes in a Docker Swarm. We have the manager node, and we have the worker node, which is the client that does the actual execution of the tasks. The manager node, very similar to other systems that we've talked about on Simplilearn, allows you to actually control and manage the actual tasks that are being executed by the worker nodes. And the worker nodes, as you can imagine, then actually execute the instructions that the manager are sending out to it. So here we have a situation where we can illustrate what would happen with a manager node sending out commands to different worker nodes. The manager is fully aware of the status of the entire swarm environment at all times. This is because of the 2-way secure communication that's going from the manager to the worker environment. The workers, as you'd expect, are accepting tasks that are being sent from the manager. So if the manager sends out a task saying that you need to be running as a MySQL environment, then the worker node will then convert to a MySQL environment. And all of these environments are scripted and controlled by you as the manager.
The actual worker nodes themselves actually have a client agent, and that client will then communicate all different states of the infrastructure back to the manager, so that any time the manager node is in full control of the entire swarm. The manager is the controller of this environment, and so you always want to be able to ensure that the manager has full access to all of the work that's happening within the swarm, and this allows you as the manager to be able to control your swarm and very quickly be able to react to any changes without having to rely on manual installations of software and hardware. And as we covered earlier on, there is a REST API that uses the communication over HTTP from the manager to the worker node. It's interesting to note that it is a REST API because if you wanted to, you could actually integrate that API into custom applications and even then create automated Docker images to be created on demand from third-party solutions that you may want to create. So one of the things that's a big advantage with having a swarm is that once you've actually created the swarm, any of the services that you create can be accessed by any node of the same cluster. One of the things you do have to do though is you have to specify what container image that you're going to use when you're creating a new service, and you can do that either through a centralized Docker Hub environment or through your own private Docker Hub environment. One of the things that's interesting is that you can set up commands and services to be either global or replicated. A global service will allow you to run a service consistently on every node within the swarm, whereas a replicated service will only push out functionality and tasks to specific worker nodes within a swarm. So you may be asking yourself, hey, isn't a service and task the same thing? No, they're kind of not in the Docker world. And the difference is a service is a description of a task or the state, whereas the actual task is the work that needs to get done. And that's the differentiator here. So what you can do as a Docker user is you actually create services, and then you can then define when you want them to start as tasks. Now, what's interesting is that when you do assign a task to a node, that same task cannot be assigned to another node. Also, what's interesting is that you can actually have multiple managers within a Docker Swarm environment. If you do, however, go down this path, you have to elect one manager to be the primary manager and the other managers to be secondary managers. In many ways, those secondary managers are really similar in concept to worker nodes, in which they have the capability of a manager, but they are dependent on that single primary manager to be able to provide the right instructions and for services and tasks to the entire Swarm environment. So if we kind of recap some of these, we have a command line interface, which allows us to create and connect via APIs. And that those APIs that we connect to in our Swarm environment allows us to do orchestration via tasks and services. The task allocation allows us to allocate work to tasks via their IP address, which allows them to execute them on the work. And then the worker nodes themselves have to connect to the manager node to be able to check for when tasks come in so that they are keeping a consistent communication back and forth across the entire swarm. And then the final stage is to actually execute the tasks that have been assigned from the manager node to the worker node so that you have a successful execution of the solution you're looking to build. All right, so with that said, let's go ahead and we're going to do a demo. So we're going to go ahead and going to do a demo and showing how you can run Docker Swarm. For this, you'll need to have both a virtual environment running your manager and your working environment. So here we have our worker and here we have our manager. So we're just going to open up terminal window and we're going to go into the manager for terminal window. So the following command here is used to initialize Docker Swarm. We're just going to type this in. So sudo docker swarm init. And we put the IP address for the network we're connecting to. And we'll put in our password. And here we have now connected. And this is our manager node. And what we want to be able to highlight is the specific token which identifies the Docker Swarm environment. And this is our token right here. So we're going to copy that because we'll need to use that for our worker environment. So here we are in the worker environment and we'll use the token that we just copied as a way to be able to connect to the manager and connect to the Docker Swarm environment.
And so sudo, we'll paste in the Docker Swarm and we'll join that. And now here we shows that we have joined the Swarm environment as a worker. And now that we're in the manager, we can actually show that we actually have that worker in the environment. So there's Docker node ls to list out all of the items in that environment. Sorry, we actually did that in the wrong area. So we're on the right, sudo docker node ls to list out all the nodes in the swarm. And there you are. You see we've actually connected the worker to the manager node, and both are active, and the manager is the leader and the worker VirtualBox is in the swarm. Okay, we're going to go ahead and create a new service. So Docker Swarm create, and we're going to just change the name to Hello World for the new service, and we're going to use the Alpine image from docker.com. Takes just a moment for it to run. There we go. And there we go. Services converged. So what we have now is a new service that has been created. Let's go ahead and we'll list out the services. And here we have our new Hello World service. And we go ahead and check the Docker containers, and we're going to do Docker PS, and here's our Alpine. It's running the latest image, and that's the Docker container ID. And we can see that it was just updated. And so what we're going to do is use the same command in the worker node and make sure everything is working over there. So go over to our worker, paste that in. So what we see here is there is no image or container created because it's not in the worker node. It would be in the manager node. So we can go ahead and create the new service. And we'll make the mode global, and that way the service is available across all of the swarm. So we're just going to execute that work. Takes a moment. And there we are. Done. Work has been completed. And we have the two different IDs, which shows the two different services running. And if we go back to the worker mode and we run sudo.docker ps again, and there we are. Now we see that we have the Hello World new virtual environment has been added with the image of Alpine. And we also have the new token ID for that. If we want to kill a node from the swarm, we can use the following command, which is sudo docker swarm leave -- force. And that will force the node to leave the swarm. Today we're going to cover Docker Compose. So in this session what we're going to do is we're going to go through what Docker is, and then by extension what Docker Compose is and how it improves the performance of Docker, what the benefits of working with Docker Compose is. We are going to cover as well what the difference between Docker Compose and Docker Swarm is, because the two products are similar but they have two different types of job. And at the end of this presentation we'll take you through some basic commands that allow you to get up and running working with Docker and Docker Compose. Finally, after this presentation, we'll do a brief demo that allows you to get up and running using some of these commands to do your own Docker Compose environment. So let's get started with Docker Compose. So first of all, we have to kind of cover what Docker is. So Docker has come as an evolution of technologies that started with virtual machines, VM machine. And a VM machine allowed you to run a complete operating system and its environment on your own computer, in your own operating system, without it interfering. The problem was that it was very heavy and complex, and in contrast, Docker is a much more lightweight and more flexible environment that you can automate with scripts. So we have to remember that the container itself is just software, and it has dependencies that run within that application that are managed by Docker. So if we have a look at the way Docker is broken out, first of all we have the Docker image, and we have the Docker image created by a Docker file. And the Docker file is a text-based script, and that text file within Docker file actually
actually has all the commands that allow you to run the appropriate technologies within the Docker image. So the Docker image allows you to be able to have a wide group of people consistently run the same environment. And if you want to be able to share that Docker image effectively, you would do so by uploading to Docker Hub. And Docker Hub can be available either publicly through the public Docker Hub website, or you can actually set up your own private enterprise Docker Hub to share your own images across your own network. And then from Docker Hub, people can then pull their own Docker image and build new containers that are consistent on the original Docker container that you created. So it's a great way of being able to have your entire team scale up easily and effectively. So one of the questions that will come up though is, what if you want to use 2 containers in a single service? And an example of this might be like a web server that is using a database, but the database may be in one container and the web server may be in another container, which is very typical for your own web and database infrastructure. So very similar scenario, but how would you do this with Docker? So by using just Docker itself, it's actually very difficult to do this. You can do it, but it's just very time consuming and just not a very good use of your productivity. But with Docker Compose, you can actually do the whole process quite quickly and easily, and hence the reason why we have Docker Compose, to allow you to have 2 or more Docker containers running in the same environment, being able to communicate as if they were running in a production environment. So let's dig into what Docker Compose is. So let's consider a scenario that you'd have today. So Myntra is a fashion website similar to Amazon, and you would go to Myntra with your web browser, and on that website you would go through a number of activities such as logging into your account, browsing a catalog, you'd have your checkout application server, and you go through the typical process of building out an application. Behind each of these services are different products, such as you'd have an account database, you'd have a product database, different checkout processes, and these would all be run behind the scenes. And each of these can be considered a microservice. So the more microservices you build into your environment, the more complexity you're adding, and the more of value it would be to have each of these services in their own container. But as a developer, you want to be able to jump from one container to another container, so your login account can then be passed on to your product catalog and then be able to move through the whole process. So the environment that you would see today would be more like what we're showing right now, where you'd have your server and your database, and you may have a server running on Apache Tomcat or SQL Server. You'd have different databases, and you'd want to be able to have each of those in their own containerized environment. So the way that Docker Compose runs is that it works as a single service. So you have the Docker Compose running multiple containers, but the perception is of a single service run. The thing that's great though is that each of those containers will run in isolation, but they can interact with each other. So unlike a normal Docker environment where you have multiple Docker images running completely in isolation of each other, these are images that will run in isolation but can interact with each other. The Docker Compose files are very easy to write. They're all written with a scripting language called YAML, and YAML is an XML-based language. It actually stands for yet another markup language, but it's an XML-based language and it's very easy to use. The great thing about learning YAML is that a lot of open source tools in the DevOps environment use YAML as the scripting language. And then finally, in Docker Compose, as a user, you can actually go in and trigger all your services within the containers to start with a single command. As you can imagine, this dramatically reduces the amount of work that you as a developer have to do. So let's take an example of if you're running a container, one with a Nginx server and one with a Redis database. You can create a YAML Docker Compose file that actually has the instructions on the containers needed to build out both environments. And then you can run each of those environments separately, but have them connected as a single service. So the benefits of Docker Compose is that you have a single host deployment environment. You can run this all on one piece of hardware. You can have a quick and easy configuration using YAML scripts. The productivity that you get as a developer significantly increases because you're not having to have time wasted trying to configure just traditional Docker containers by themselves. You now have a way of being able to interact with those containers. And then finally, security is at the center of all of these containers. So each of those containers are completely isolated from each other, and they are controlled with the same level of security that you'd have with a traditional Docker image. But there is a question here around Docker Compose. Isn't it similar in concept to Docker Swarm? Because at a high level, it kind of seems like both do the same thing. And the answer is, well, actually, no, they're different. There are similarities, but there are also differences. And particularly for a developer, these differences will really start coming out in scale as you start working on your solutions. So let's look at Docker Compose. So Docker Compose will allow you to create multiple containers on a single host. And that's the important part, having a single host, which is maybe your development PC. With Docker Swarm, it also allows you to create multiple containers. However, you have to manage those multiple containers on multiple hosts, which makes a lot of sense if you're running an operations environment, but not so much if you're doing a development environment. And Docker Compose is scripted with YAML, which is very easy for you to be able to control your scripts. Docker Swarm doesn't have a scripting technology like YAML, so it's a little bit harder to work with. So what we have here is just some basic commands that allow you to get up and started working with Docker Compose. In our next demo, we're actually going to take you through how to use all of those commands. So we're going to go ahead and do a demo on how to use Docker Compose. The first thing you want to do is check that you have Docker installed. So what we're going to do is we're going to open up the command window and we're going to type in Docker. You'll be able to see now that we have Docker installed. If you don't have Docker installed, go ahead and install Docker. You can go to Google search to install Docker and they'll give you the instructions for that. We also have videos that we've already done. If once you have Docker installed, then you want to do a Google search on Docker Compose or go to the docker.com website and select for the Compose section and look for the install Docker Compose instructions. So we already have another tab which has the instructions already installed. You'll see on the left hand side there are a number of Docker tools. You want to expand the Docker Compose section, select install Compose, and then on the right hand side you'll have different install options for Mac, Windows and Linux. If you're installing on those platforms, make sure you're copying the correct command lines. There's a couple of command lines you want to copy. Copy the first one over and we paste that in, and it's going to go ahead and download all of the files for Compose. It takes a while, but we have to get another file, so while it's downloading we'll go get the other command line. Just go back and grab it real quick. It was a little fast there, but we'll copy that over. There was a second command instruction and post that command. Yep, there's the command right there. And that will apply the appropriate binary. And once you've done that, you can actually go ahead and validate that you have the correct version of Docker Compose installed. And for that, you want to write the command docker-compose space -- version. And that will then give you a version build. Once you know that you have a version build, that means that you have everything installed correctly on your machine. So you can see here that we have a version number, which means we have everything installed. You might see a different version number depending on how old the video is when you're watching it, but we're using very little content at the moment. And just go ahead and clear the screen. And now what we're going to do is create a folder where we're actually going to install the YAML file that will have the instructions for our Docker Compose environment. So we're moving the cursor to the desktop, and on the desktop we're going to create a new folder and using the mkdir command, and we'll call this one Docker Compose F for file, and then we'll move the cursor into that new folder by using cd command. And now we are in the folder called Docker Compose F, and you can go look at your desktop and you'll see it's there. And now you want to select #touch docker-compose.yml, and that will actually create the new YAML file for you, and you can use the ls list command, ls docker-compose.yaml, and that'll allow you actually now to step in and edit that file. So let's go ahead and hit return, and that'll allow us to go in and edit the file. So now I'm in the editor, and I'm going to write some instructions. So I'm going to put a couple of mistakes in these instructions so we can see how Docker Compose catches those mistakes. But most of this is going to be fairly correct, so you can just type this out. So we're going to start with services : then we'll do web : and then we'll create image : and we'll do Nginx, and then we'll do a database : and we'll call the image Redis. And so what you can see, because we have two reference images, we're actually calling two different images, two different containers that will be created by Docker Hub. So what we're going to do is where we can actually show you how that's pulling in. You can go to Docker Hub, and you can actually see the references to the images that we've just created. So go to Docker Hub, which is hub.docker.com, and you'll see that Nginx, Redis, those are the default names for the images. So you could do other images like HTTP for Apache web server if you wanted to. There are a lot of images in Docker Hub, so certainly have a lot of fun building tools from that environment. So we're going to save those files in the Docker image, and we're just going to do :WQ to exit this screen. Save the text. Let's go and run our YAML file, and you'll see the two different error messages that will come up. So we're going to do cat docker-compose.yml, and here we have a display of the text that we just wrote. And now let's go check the validity of the file that we just created. So we'll do docker-compose config, and we should get an error message. And there we are, error message. And the reason why we have an error message is because the spacing is not correct in the YAML file itself. So let's go to the actual YAML file that we created. Let's go through, and we're going to use just the file finder, and you'll actually open up the YAML file in your text editor, your favorite text editor. And here we have the code that created it. And let's use the correct spacing so that everything is spaced out appropriately in the image. And so this is the spacing that you'd expect to see, a line between surfaces and the first image, and the first image is a tab in, and then it references what the image is. And let's go ahead and clear the screen, and we'll see whether or not we've got that all correct. Let's clear the screen, and we're going to check that everything is running correctly. And we're still getting an error message, and the reason why we're getting another error is that there's still a config error in the actual YAML file. So one of the things you have to do when you're creating a YAML file for Docker Compose is you actually have to have the appropriate version number in there. So what we have to do is we have to go and find which is the appropriate version. And there are three major versions, 1, 2, and 3, depending on the age of Docker that you have installed on your computer. So if you have the very latest version of Docker, 18 and newer, you would put 3.7 as the version number. And what we're going to do is we're going to just check on the version that we have installed. And so we just clear the screen, and then we'll just do Docker version. And what we have is our version of Docker is 17.12. Now this is the version of Docker, not Docker Compose. It's your main Docker environment. And so if we go back to our web browser, we'll actually see that version 17 should align with version number 3.5. Yep, there we are, version 3.5. So what we want to do is go back into our YAML file. And the very first line that we want to put in above the services is the version number. And that version number we're going to put in is 3.5. So we type in version, and we put colon, and then version number is in quotes, and you save that. And now what we can actually do is we can actually go ahead and use the single line instruction to run both of these two images that we've created, because everything is configured correctly. But just one note, you'll see that the version number is actually at the bottom of the list. And that's just the way that Docker Compose works. It pulls out the services and the images that you'd create, and then puts the version number at the bottom of the list. So in the presentation, we talked about how you can use one line to trigger 2 or more images. And so to do that, we're going to do sudo docker-compose up-d. And it's going to create the 2 environments. We have the web environment and the database environment. And let's use sudo docker ps to actually list out all the processes that are running right now. And there we are. We actually see all of the images that are running. We have the names, the commands, the images, and everything's up and running. And if we want to close both of those images, we can actually use a single line of command as well. And that command will be sudo docker-compose down. And that closes both of the images. And we can see that all the databases and the web services images have been closed, and sudo docker ps will actually list that there is nothing running. And that's how to use Docker Compose.
In this session, we're going to cover what Kubernetes is and why you would want to be using it within your DevOps team. So let's get started. We're going to break up this presentation into 4 key areas. We're going to talk about life before Kubernetes, which some of you are probably experiencing right now. What is Kubernetes? The benefits that Kubernetes brings to you, particularly if you are using containers in a DevOps environment. And then finally, we're going to break down the architecture and working infrastructure for Kubernetes so you understand what's happening and why the actions are happening the way that they are. So let's jump into our first section of life before Kubernetes. So the way that you have done work in the past, or you may be doing work right now, is really building out and deploying solutions into 2 distinct areas. One is a traditional deployment where you're pushing out code to physical servers in a data center, and you're managing the operating system and the code that's actually running on each of those servers. Another environment that you may potentially be using is deploying code out to virtual machines. So let's go through and look at the 2 different types of deployment that you may be experiencing. When you have applications running on multiple machines, you run into the potential risk that the setup and configuration of each of those machines isn't going to be consistent and your code isn't going to work effectively, and there may be issues with uptime and errors within the infrastructure of your entire environment. There's going to be problems with resource allocation, and you're going to have issues where applications may be running effectively and not effectively, and not load balanced effectively across the environment. The problem that you have with this kind of infrastructure is that it gets very expensive. You can only install one piece of software, one service on one piece of hardware, so your hardware is being massively underutilized. This is where virtual machines have become really popular. With a virtual machine, you're able to have better resource utilization and scalability at much less cost. And this allows you to be able to run multiple virtual machines on a single piece of hardware. The problem is that VMs for virtual machines are not perfect either. Some of the challenges you run with VMs is that the actual hardware and software needed to manage the VM environment can be expensive. There are security risks with VMs. There are security risks with VMs. There have been data breaches recorded about solutions that run in virtualized environments. You also run into an issue of availability, and this is largely because you can only have a finite number of virtual machines running on a piece of hardware. And this results in limitations and restrictions in the types of environment you want to be running. And then finally, setting up and managing a virtualized environment is time consuming. It can take a lot of time, and it can also get very expensive. So how about Kubernetes? Well, Kubernetes is a tool that allows you to manage containerized deployment of solutions. And inherently, Kubernetes is a tool that is really a next level maturity of deployment. So if you can think of your maturity curve as deploying code directly to hardware in a data center, and then deploying your solutions to virtual machines, the next evolution of that deployment is to use containers and Kubernetes. So let's kind of go through and look at the differences between a virtual machine and Kubernetes. And we've got a few here that we want to highlight, and you'll get an understanding of what the differences are between the two. So first of all, with virtual machines, there is inherently security risks. And what you'll find as we dig through the architecture later in the presentation is that Kubernetes is inherently secure. And this is largely because of the legacy code, the legacy of Kubernetes and where it came from. And we'll talk about that in just a moment. But Kubernetes is inherently secure. Virtual machines are not easily portable. Now, with that said, they are technically portable. They're just not very easily portable. Whereas with Kubernetes, it's working with Docker container solutions. It is extremely portable. That means that you can actually spin up and spin down and manage your infrastructure exactly the way that you want it to be managed and scale it on the demands of the customers as they're coming in to use the solution. From a time-consuming point of view, Kubernetes is much less time-consuming than with a virtual machine. A few other areas that we want to kind of highlight from differences. Virtual machines use much less isolation when building out the encapsulated environment than Kubernetes does. For instance, with a virtual machine, you have to run hypervisor on top of the OS and hardware. And then inside of the virtual machine, you also have to have the operating system as well. Whereas in contrast, on a Kubernetes environment, because it's leveraging Docker container or container-like technologies, it only has to have the OS and the hardware, and then inside of each container, it doesn't need to have that additional OS layer. It's able to inherit what it needs to be able to run the application. This makes the whole solution much more flexible and allows you to run many more containers on a piece of hardware than versus running virtual machines on a single piece of hardware. So as we highlighted here, VMs are not as portable as Kubernetes, and Kubernetes is portable, directly related to the use of containerization. And because Kubernetes is built on top of containers, it is much less time consuming because you can actually script and automatically allocate resource to nodes within your Kubernetes environment. This allows the infrastructure to run much more effectively and much more efficiently. So this is why if we look at our evolution of the land of time before Kubernetes, why we are running into a solution where Kubernetes had to come about, because the demand for having more highly scalable solutions that are more efficient was just really a natural evolution of the software deployment model that started with pushing out code to physical hardware and then pushing code out to virtual machines and then needing to have a solution much more sophisticated. Kubernetes would have come about at some point in time. I'm just really glad it came about when it did. So what is Kubernetes? Let's dig into the history of Kubernetes and how it came about. So in essence, Kubernetes is an open source platform that allows you to manage and deploy and maintain groups of containers. And a container is something like Docker. And if you're developing code, you're probably already using Docker today. Consider Kubernetes as the tool that manages multiple Docker environments together. Now, we talk a lot about Docker as a container solution with Kubernetes. The reality is that Kubernetes can actually use other container tools out there, but Docker just simply is the most popular container out there. Both these tools are open source. That's why they're so popular. And they just allow you to be able to have flexibility in being able to scale up your solutions. And they were designed for the post-digital world that we live and exist in today. So a little bit of background, a little bit of trivia around Kubernetes. So Kubernetes was originally a successor to a project at Google, and the original project was Google Borg. Google Borg, it does exactly what Kubernetes does today, but Kubernetes was rewritten from the ground up and then released as an open source project in 2014 so that people outside of Google could take advantage of the power of Kubernetes containerization management tools. And today it is managed by the Cloud Native Computing Foundation. And there are many companies that support and manage Kubernetes. So for instance, if you're signing up for Microsoft Azure, AWS, Google Cloud, all of them will leverage Kubernetes. And it's just become the de facto tool for managing large groups of containers. So let's kind of step through some of the key benefits that you would experience from Kubernetes. So we have 9 key benefits. The first, it is highly portable portable, and it's 100% open source code. And this means that you can actually go ahead and contribute to this code project if you want to through GitHub. The ability to scale up the solution is incredible. What's the history of Kubernetes being part of a Google project for managing the Google network and infrastructure kind of really sets the groundwork for having a solution that is highly scalable. Out of the high scalability also comes the need for high availability. And this is the desire to be able to have a highly efficient and highly energized environment that also you can really rely on. So if you're building out a Kubernetes management environment, you know that it's going to be available for the solutions that you're maintaining. And it's really designed for deployment. So you can script out the environment and actually have it as part of your DevOps model so you can scale up and meet the demands of your customer. Then what you'll find is that the load balancing is extremely efficient, and it allows you to distribute the load efficiently across your entire network so your network remains stable. And then also the tool allows you to manage the orchestration of your storage. So you can have local storage such as an SSD on the hardware that the Kubernetes is maintaining. Or if the Kubernetes environment is pulling storage from a public cloud such as Azure or AWS, you can actually go ahead and make that available to your entire system. And you can inherit the security that goes back and forth between the cloud environments. And one of the things you'll find consistent with Kubernetes is that it is designed for a cloud-first environment. Kubernetes as well is that it's really a self-healing environment. So if something happens or something fails, Kubernetes will detect that failure and then either restart the process, kill the process, or replace it. And then because of that, you also have automated rollouts and rollbacks in case you need to be able to manage the state of the environment. And then finally, you have automatic bin packaging, so you can actually specify the compute power that's being used from CPU and RAM for each container. So let's dig into the final area, which is the actual Kubernetes architecture. And we're going to cover this at a high level. There's actually another video that you can that Simplilearn has developed, which digs deeper into the Kubernetes architecture. And so the Kubernetes architecture is a cluster-based architecture, and it's really about two key areas. You have the Kubernetes master, which actually controls all of the activities within your entire Kubernetes infrastructure. And then you have nodes that actually are running on Linux machines that are controlled by the master. So let's kind of go through some of these areas. So if we look at the Kubernetes master to begin with, we'll start with Xcetrid. This is a tool that allows for the configuration of information and the management of nodes within your cluster. And one of the key features that you'll find with all of the tools that are managed within either the master environment or within a node is that they are all accessible via the API server. And what's interesting about the API server is that it's a RESTful based infrastructure, which means that you can actually secure each connection with SSL and other security models to ensure that your entire infrastructure and the communication going back and forth across your infrastructure is tightly secured. Scheduler goes ahead and actually, as you'd expect, it actually manages the schedule of activities within the actual cluster. And then you have the controller, and the controller is a daemon server that actually manages and pushes out the instructions to all of your nodes. So the other tools really are the infrastructure, and you can consider them the administration side of the master, whereas controller is the management. It actually pushes out all of the controls via the API server. So let's actually dig into one of the actual nodes themselves. And there are three key areas of the nodes. One is the Docker environment, which actually helps and manage and maintain the container that's actually inside of the node. And then you have the kubelet, which is responsible for information that goes back and forth. And it's going to do most of the conversation with the API server on the actual health of that node. And then you have the actual Kubernetes proxy, which actually runs the services actually inside of the node. So as you see, all of these infrastructure infrastructures are extremely lightweight and designed to be very efficient and very available for your infrastructure. And so here's a quick recap of the different tools that are available. And it really breaks down into two key areas. You have your Kubernetes master and the Kubernetes node. The Kubernetes master has the instructions of what's going to happen within your Kubernetes infrastructure. And then it's going to push out those instructions to an indefinite number of nodes that will allow you to be able to scale